Welcome to Ask and Learn.
They want us to show that a finite poset can be reconstructed from its covering relation. So let's go ahead and start proof. So they give us a hint for this, and they say to show that the poset is the reflective transitive closure of its covering relation. So first thing we should do is assume that SR is a finite poset. Now I'm going to let C be the ordered pairs for the covering relation of our poset. So the first thing we can show is that this poset is our reflexive closure. So let's do that to start. So now we want to suppose that AB is some ordered pair in our set C. Well, by the definition of our ordering or of our covering relation, AB has to be an element of our set S. And we know that since SR is a poset, it is reflexive, which means both AA and BB will be an element of R. Thus, it is it is the reflexive closure. I don't know why I spelled reflexive like that up there. So reflexive closure. All right. Now let's go ahead and do the transitive. The reflexive closure. This is of our covering relation. So we should say that. All right. Now let's do the transitive part. And actually, it wouldn't hurt to say what we're doing for here. So maybe right here. So we can just say something like reflexive covering, just to kind of tell the reader or prompt them as to what we'll be doing. And then down here, we'll say transitive closure. Oh, I don't know why I said covering here. It should also be closure. All right. Now we're going to start similarly as to we did before. So we're going to assume that there's two ordered pairs. So now suppose that we have the ordered pairs A1, A2, and A2, A3. And these are both ordered pairs in C. Now what we know is C has to be a subset of R. which is going to imply that A1, A2 are going to be, well, A1, A2, and A2, A3 are going to be elements of R, and due to SR being a poset, it is transitive, and thus A1 to A3 is an element of R. And actually, we should probably say why this is the case right here, that it is a subset. And that really just comes from the fact that all of the ordered pairs, again, by the definition of C, should be in S. And so any relation that we have on S should be on R, and then if it was in C, then it also must be in R. And that's just kind of by like the definition for the covering set that we have. All right, so now we have that part there. But we should also suppose, so we have some thing in R. So now suppose that the ordered pair B1, B2 is in R. And we want this to be such that there are no B in S where if B1, B2, B2, B3, dot dot dot, all the way up to Bn minus 1, Bn are elements of R, then there does not exist. So 1 second. So we have that if all these are in there, there exists no B in our set S where if all those are in R, B, J, little b, B, J plus 1 is not an element of C. And we want this for J an element of 1, 2, all the way up to n minus 1. So let me just kind of explain what that's saying there. So it's really saying that this set here is, as long as we can make it, going from B1 to Bn, and that there is nothing that gets in the middle of it. Or actually, maybe for this we should say R, like that instead. So this is the maximal length that we can make for this, which, so we can ensure this. So we can ensure this due to R being, or due to our poset being finite. All right. And we know each of the bj plus 1s are elements of R due to posets being transitive. So we have that. And now what this means is, now by the definition of our covering relation, each bj plus 1 must also be an element of C. So since that's the case, that means, so this implies that our poset is the transitive closure of our covering relation. And since we have that it's the reflexive and the transitive closure, we've proved what we wanted to. So let's kind of just walk through what we did again really fast. Oh, but at the end you can put your little proof box and a smiley face. So the first thing we did was tell everyone that this is a finite poset, and then we defined C to be all the ordered pairs for our covering relation of this poset. So the first thing we wanted to show was that this was the reflexive closure of it. So we went ahead and chose some arbitrary element in our ordered pair or the set of the ordered pairs for the covering relation, C, said everything was in C, showed by that it had to be reflexive, so it was the closure there. And then here we just took two arbitrary elements in C that did not have the transitive property of it, but since we know that our ordered pair set should be a subset of the ordered pair on our regular relation, that both of those should be in R, and since we had a poset, that means A1 to A3 had to be also in there due to it being transitive. And then this part here was to show that we can reconstruct any of the chains in R as long as we can find some maximal chain that goes from this starting point to our ending point here. And once we find that maximal, all of these then get translated into our covering due to all of them only being of one length, because we made this assumption here that there is no B in S where this B can squeeze in between one of these. And so from that, then we can say we can reconstruct all of them. So that was pretty much what we did for that.